Hi everyone and welcome back to the channel. So now in this video you can officially consider this the start of electromagnetism, which starts with the idea of the magnetic effect of a current. Now I'm going in a slightly different order than what the syllabus specifies, which in my opinion is strictly speaking not the best way to start teaching this unit. So the first thing that we are talking about is the magnetic effect of a current, and the idea associated with this is that a magnetic field is basically associated with any current. So a magnetic field would be set up around a current carrying conductor. So if we have a wire or anything for that matter which has current, there would also be a magnetic field set up around it. Now a simple diagram to show this idea. So let's say this is a piece of paper or cardboard with a hole in the middle through which a wire passes, and that takes current in such a direction. So if I were to place a plotting compass here, which we know is the best indicator for whether a magnetic field actually exists or not, and as I move it around here, I'll see that it points in different directions. That is basically telling me that there is a magnetic field strength associated with the current in this wire. So when we talk about this, we'll also often be given questions like these where I would be given the direction of current in a wire, and I would have to make the magnetic field lines for it. And for that purpose, this is going to be one of the many rules that you'll be using in this chapter, is the right hand grip rule. So the right hand grip rule. And the first one that we are doing is for a straight wire case. So this is for a straight wire. The rule is pretty self-explanatory, but still let me write down something as to how we have to use this to find the direction of the magnetic field here. So for a straight wire, we'll just use a right hand's thumb and point it in the direction of the current. However, the other 4 fingers on our hands, or 5 if you're Hrithik Roshan, could give the direction of the field, right? So let's also see this using a example. So this is your current, and however the other 4 fingers wrap around, this is the direction of the field. Now let's see how this is going to be used. So in the example above, we had current flowing upwards. Now it wasn't really strictly speaking upwards. How we talk about this is in terms of 2 symbols. Now let's say that we have the current like this here. So I'm looking at this from the top here. And this is how the current appears to me. So it's not just going upwards. If I'm looking at this directly upwards, I would say the current is coming out of the card towards me. Now how I show this is if I just imagine this as a arrow like this. So for example, if this is an arrow, and let's say the other end of the arrow is like how you have that bow and arrow in, for example, movies or something. And if you're looking at this current coming out of the page, then at this point, this is what you'll see. All you'll see is a dot. And if you're looking at the current from the other side, this is going to be coming, or rather going into the page. So this is sort of like symbols that we use, that this is current into the plane of the page or into the plane of the screen that you're watching this on. So this is current out, and this is current in. Now for example, if I'm looking at this from the top, then this would appear to me as if this is current coming out of the page. So I would draw it like this. And this dot in the middle shows that this is current out of the page. And now I need to make the field lines. So almost always now in recent papers, this is always given to you that what current out and what current in is. So this is current into the page, but it still doesn't hurt to know this anyway. So with this being current out of the page, all I need to do is I need to position my thumb such that my thumb, which is basically representing the current, is also out of the page. So I want all of you to do this right now. And again, make sure that you're using your right hand because that's what the rule says. And according to that, when you curl your fingers, the other four fingers, this will tell you the direction of the current. So for example, in this case for me, and it should also be the same case for you, it's curling anti-clockwise. So how the field would be in this case is like this. So you will have field lines like so, right? So you'll make these and the direction would be anti-clockwise like this. Two arrows are more than enough to show the direction. Even one is enough, but two is just, it's more complete. Now, the first thing is you should know that for a current carrying conductor, a simple and a isolated current carrying conductor, the field lines are supposed to be concentric circles. When you draw it like this is what gets you 1 mark. This is often asked for 3 marks. The second one is a correct usage of the right hand grip rule to assign directions to the concentric circles. And the third mark is for this, that because you know, as we previously talked about this in the chapter of magnetism as well, the relative spacing of the field lines show the direction of the magnetic field strength. Now we know that this is the source of the current, and going away from this, the magnetic field strength is supposed to fall off. So when we are making this, our circles should progressively be getting bigger to show that the magnetic field strength is decreasing. Now for example, if I make it like this, this and this spacing seems the same. And if I drew it like this, the examiner would deduct marks. So all I need to do is to expand this circle slightly more so that it becomes obvious that the spacing is increasing, right? And again, I don't need to use the right hand grip rule again and again. I can already tell whatever the directions are. And then the third circle is going to be even further away. So something like this. So this shows increasing spacing. So this is the field pattern for current out of the page. So again, these are the check boxes that you must be ticking off, which is concentric circles. Concentric mean circles with the same center. So concentric circles, done. The direction of the arrows that we got from the right hand grip rule, done. And then increasing distance between the circles, increasing spacing, done. Right, so that's how you draw field patterns for isolated current carrying conductors. Now what if the current was going in the opposite direction? Then we know that if you're still looking at this from the top of the page or the top of the card, then the same case is going to become current into the page because current is going into the plane of the card here. Let's look at how that would look. Although this is pretty easy, there are really only two cases possible, current out of and current into, so you can probably guess what the change is going to be. But let's draw this anyway here. So looking at this from the top, current is going into the plane of the paper. How would the field pattern change? Now what would happen is if I were to make pattern again, so I know that this time it would not be a dot, it would be a cross because this is current into the page. So let me make a cross here for this. So this is current into the page, and now I know that if I have my thumb pointing inwards in towards this cross and I curl my fingers, these now curl clockwise. So it's going to be the same field pattern as above, only now the direction of the arrows is going to be reversed. So it's going to look like this. So curling clockwise, so just the direction of the arrows change like this. So this is what the field patterns look like for isolated current carrying conductors.
But what would happen if we bring two of these conductors inside the field of each other? So what I mean to say is basically if I have a card and inside these we have parallel current carrying conductors. Now how would the field look like? So parallel current carrying conductors, which I'm writing as CCC. So let's look at the first case where we have current carrying conductors like these. So both of these are parallel current carrying conductors, and if viewed from top, both are taking current out of the page. Now I know what the individual fields look like for each of these. So if I were to make a few field lines, that would look like this. So as per the right hand grip rule, so with my thumb pointing out, my fingers curl anti-clockwise. So this is how the field pattern looks like for this. And similarly for the other wire, it would look exactly the same, with the field of this also looking exactly the same way. And if you might recall, and if you look at your diagrams that you've just made, I made the third one for this as well. And I'm going to make the third one for this here as well, but I need to think about something. Now, if I were using the right hand grip rule here, I could see that my fingers were curling anti-clockwise, and similarly here, they're also curling anti-clockwise. So the third circle would look like this and this, obviously keeping that point regarding increasing spacing in mind. But if you look at the center here, then basically at the center, this upward and this downward field would cancel out, and there would be no field right between them. And this anti-clockwise field like this and this anti-clockwise field like this, they would join up in a pattern that looks like this, with these being the directions of the field lines. And upwards from here, so like this. Now there is no technical way to understand this. I mean there is, but it's a bit complicated. So both of these currents would basically exert forces on one another. And the idea is very simple. It's what we started this video off with, which is that if there is a current carrying conductor, it would have a magnetic field around it. And similarly also for the other current carrying conductor, there would be a magnetic field around it as well. And when both of these magnetic fields will interact, they will exert forces on each other. And this idea will be explored in greater detail in the next video. But for now, you can imagine that your magnetic field lines are basically like elastic bands. And these elastic bands are basically going to collapse in on itself, and they're stretched right now. So if you think about this larger band, if this is stretched and if I let go of it, then you know that this would collapse inwards, this would collapse inwards. And in this case, the forces which would be exerted by both of these conductors on each other would be in the same direction. And these are what we basically call like currents, because both of these are taking current in the same direction. So the idea is that since these wires, these current carrying conductors would move towards each other, the rule here is that like currents attract. Now this is separate from what we talked with regards to charges and poles, because they're like poles or like charges used to repel, but like currents attract. Similarly, if I have another case where I just reverse these and both of these take current downwards, the same thing would happen, and you can probably guess. Only now my fingers, because this would be a cross in the middle, my fingers would be curling clockwise, and the only thing which literally changes is the direction of the arrows. So in that case, the field pattern would look like this. So this is the second possibility we are talking about. So this is what it looks like. Both of the currents carrying conductors carrying current downwards, and the fingers would go clockwise. Again, right at the center, you can see this and this direction are opposite, so the fields cancel out here, and otherwise they join up in one field line that looks like this. So the thing to remember from this drawing is that like currents attract. So the only other case which is left is basically of unlike currents, where you have one current carrying conductor carrying current upwards, the other one carrying it downwards. So let's have a look at how the field patterns would look like in that case. You can also pause the video and think about this for yourself to see whether your thinking is actually correct. So with this one, I know that one of these is carrying current into the page. This is a cross. This one is carrying current out of the page. This is a dot. So if I think about it like this here, and I'll paste the actual diagram in a while. So this is my cross here. This is the dot. So with the cross, I know that this is current into the page. So my thumb points inwards, and you will see that your fingers are curling in this direction. And for the other one, you will see that your thumb would point out and the fingers curl in the opposite direction, which is like this. So as opposed to what happened previously in the center here, both of these fields would reinforce each other, and the fields would add up because both of these are downwards. So in the middle here, the field would be even stronger because both of the individual field lines are in the same direction. So the field is stronger, and you know the way to present that is basically using a decrease in spacing, because a decrease in spacing shows that the magnetic field strength is increasing. So this is how the field lines look like. So this is the shape that we have. Again, the field lines add up here, which is shown by that decrease in spacing as opposed to how it was without the other one here. And this field line basically becomes sort of egg-shaped. And how you can understand it is this. Again, I would suggest not really going too much into its understanding, because what your syllabus requires you to know is just how the field lines look like. If you really try to get into why the field lines are like this, you may end up confusing yourself. But anyway, for anybody who's curious, I know that for this one, the field line would be like this. And this field line is in that direction, the opposite direction. But because this is such a huge distance away from here, it's going to cancel out only partially, which is shown by this increase in spacing. So the magnetic field strength here is only marginally weaker than whatever it is here. And similarly also for this case, right? So you have these egg-shaped field lines for either of these. Again, if you think of the field lines as elastic bands, if I let go of these, which are stretched right now, these will propel the field lines, the current carrying conductors in opposite directions. So in this case, forces on both of these are acting in opposite directions. These are unlike currents because they are carrying currents in opposite directions. So I would say unlike currents repel. So that's it for this video. In the next one, we'll actually start looking at more ideas, and basically something that we touched upon here, which is that there would be a force on a current carrying conductor inside the magnetic field of another one. This is what we'll be starting with next time. So see you there.